Hi, this is Mrs. Villette, and this video is a continuation of our work with rational exponents. The last video ended with looking at the square root of x squared and what that looked like, and also the cube root of x cubed. An important thing that we learned was that if you take the square root of an even root of a power x, that should simplify to the root of x. But when you take odd roots, it doesn't matter. Now if we do it in the opposite order, so if we take the nth root of x and raise that to the nth power, this will also just give us x, even though it's even, so long as x is positive or 0. And the reason this is important is in order to be able to take an even root, the x before we even start has to be greater than or equal to 0. So we take the nth root first and then raise it to the nth. We think of those two operations as sort of undoing each other, but it's not a full undo, it's only a partial undo. So in this case, it's only for x's that are positive. But again, if we have odd roots, doesn't matter. You can take the nth root and then the nth power, and you just get x. So the one we really need to pay attention to is this case where we are taking even roots of variables. So we're going to simplify the following expressions, leave answers in radicals, and use absolute values when necessary. So let's see what that looks like. Our first example is 64x to the 4th, y squared, z to the 10th. So we are taking an even root of variables. With the numbers, we just do this the normal way. So the square root of 64 is 8. The square root of x to the 4th would be x squared, but we would put it in absolute value. I'm going to go ahead and do all my variables together in the same absolute value. The square root of y squared would be y, and the square root of z to the 10th would be z to the 5th. So the important thing here is that we use absolute values when simplifying even roots. Now there's one thing that I can do to make this slightly simpler, and that's to take this x squared out of the absolute value. Since this is an even exponent, it's always positive, so it doesn't need to be an absolute value. So we could say 8x squared absolute value of y z to the 5th. Okay, on B we're doing a cube root, so if it's a cube root, we don't need to worry about absolute value. So when we see that cube root, no absolute value is needed. So we just run through and we do cube roots. So cube root of 64 is 4. The cube root of x to the 6th is x squared. And the trick that you can use here is you're dividing the exponent by 3. So x to the 6/3 is x squared. Similarly, y to the 9/3 is y cubed, and z to the 12/3 is z to the 4th. So when we're taking cube roots of variables with exponents, we're not cube rooting the exponent, we're dividing the exponent by the index. And that's again using this idea. If I just had the cube root of x to the 6th, that would translate to x to the 6/3. So odd index, no absolute value, so that is our simplified answer. Okay, let's look at this C example. It doesn't really seem like there's much that we can do with this C, but we could do a little bit of exponent work. We could write this as x to the 10 fifths. And the reason I'm doing that is the index of the root becomes the denominator. And then I know 10 fifths reduces to 2, so this would be x squared. Okay, now we're looking at D. Doesn't seem like there's much we can do with this. Maybe we can do the same trick we used on the last problem, which is to realize this is a square root. So this is x to the 10 halves, and x to the 10 halves, or x to the 5th. Now one thing that we would need to think about is in the original expression, we would actually need the x value to be positive. So we're going to say x has to be greater than or equal to 0 because in that original expression x needed to be positive. So if we look back at C, we don't actually need that restriction because it was a fifth root, and we can put anything we want in fifth roots. So we don't need to worry about fifth roots being positive or negative. Okay, here's part E. So 10th root of 32. This doesn't look like it simplifies much. Maybe we could do something with this 32. So let's go ahead and look at the prime factorization of 32. So we're breaking 32 down into all its prime factors. So 32 is 2 to the 5th power, and we can go ahead and rewrite that in rational exponent form as 2 to the 5/10, or 2 to the 1/2, which is the same thing as the square root of 2. And that is our simplified answer. Notice the index from the original expression went down, and also the radicand itself got smaller. So that's how this got simplified. Similar idea on F. I'm going to rewrite 9 as the square of 3. So 9 is 3 squared. Now I have 3 to the 2/4, or 3 to the 1/2, just simplifying that fraction, which is the square root of 3. Again, the index on the radical went down, and the radicand was reduced. So the last type of problem you will see where they'll say something like, assume all variables represent positive integers. And what they're trying to say in these cases is, just don't worry about this whole when do I need to put absolute values on my answers. So don't worry about putting absolute values. It's not technically the most correct thing to do, but if they say to do it, we'll do it. So we'll rewrite this as x to the 2/8, just using our exponent rules, which reduces to x to the 1/4. Normally, we would go ahead and say, hey, I just reduced an even exponent. I need absolute values. But they said, assume the variables are positive. So in this original expression, x could have really been any number. When I square it, that answer would have been positive, and then I would take the 8th root. So doing the absolute value would allow the x to still be positive or negative. But since x is positive, we can just say x to the 1/4 or the 4th root of x. Now I'm not a fan of this type of problem because it's not actually correct. The more correct answer is to say that it's the 4th root of the absolute value of x. Again, the domain of the original expression is all reals because any number squared would be positive, and the domain of that absolute value function is all reals and allows me to take the 4th root of any number that I put in. Now on this last page, we're going to do an example of using radicals and rational exponents to solve equations. And we're going to deal with these very similarly to how we would deal with something where we would solve with the square root property. So the first thing I want to do is find the variable that's raised to the exponent. So find the thing that has the cube or the 4th power. In this case, it's the x cubed. And I want to isolate that term. So I'm going to get the 3x cubed isolated by moving the 81 over to the other side. Now I want to further isolate the x cubed by dividing both sides by 3. So that gives me x cubed is 27. Next, I want to try to uncube. So I'm going to raise both sides to the 1/3 power. Or equivalently, you can say I'm going to cube root both sides, since a 1/3 power is equivalent to a cube root. The left-hand side, when I multiply the exponents, power to a power, gives me x to the 1st, or just x. And the right-hand side is the cube root of 27, which is 3. My solution set is 3, and you should go ahead and make sure you go back and check. So plug 3 into the original expression. You get 3 times 27 is 81, subtract 81, which is, in fact, 0. Okay, let's take a look at this example B. Very similar setup, except now it is a 4th power. So I want to isolate the 4th power by dividing both sides by 2. So x to the 4th equals 256. That means x is the 4th root of 256. A nice handy trick is that a 4th root is equivalent to a square root of a square root. So if you want to make it a little bit easier, do the square root of the square root of 256. So the square root of 16 and the square root of 16 is 4. And we can go ahead and check that if we do 2 times 4 to the 4th, do I get 256? And I do indeed get the correct answer, so our solution set is 4. Okay, the last example doesn't work out as nicely as the other ones, but we still use the same technique. So isolate the 4th power. X to the 4th is 9. So x would be the 4th root of 9. And we'll use the same trick we did on the last problem, which is to do the square root of the square root of 9. And the square root of 9 is 3, so that means my x is the square root of 3. If we want to go ahead and check, we would do the square root of 3 to the 4th power, multiplied by 3, see if that's equal to 27. Well, I know that this is the square root of 3 times the square root of 3 times the square root of 3 times the square root of 3. And we can see that if I do the root of 3 times the root of 3, I get 9. Something's not working out here. And root of 3 times root of 3 is not 9. Root of 3 times root of 3 is just 3. And this is 3, so 3 times 3 times 3 times 3 is 27. So yes, that works. So my solution set is simply the square root of